So our last, but most definitely not least speaker of the evening is Dr. Caoimhe Rooney, who is a postdoctoral researcher at NASA, and specifically NASA Ames, based in California. Unfortunately, Caoimhe has not managed to go over there yet, but hopefully will be soon, and is beaming into us from Belfast this evening. So yeah, take it away, please, Caoimhe. Oh, actually, sorry, I've nearly forgotten my poll. How terrible of me. So we do have another quick poll for just ahead of Caoimhe's talk, which is all about exoplanets and looking for habitable life out there. So really quick one about how likely you think it might be to find a planet outside of our solar system that could potentially contain life or harbour life, have an ability to harbour life. Great, so people are voting away. Sorry about that, Caoimhe, go ahead.
No problem. Hi, everyone. Thank you very much for hanging around till the end of this session. My talk is titled Head in the Clouds, an introduction to the perils of cloudy planets. And I'm going to give you a bit of a background into the discovery of planets outside of our solar system, their characterization, that's understanding what they're made of, and why clouds are troublesome on planets all over the galaxy, not just here on Earth. Okay, so but before we start, a little bit about me. I'm from Belfast. I studied my undergraduate degree in maths at Trinity College in Dublin before doing a PhD in applied maths at the University of Oxford. And I'm now a NASA postdoctoral program fellow at NASA Ames in California. But as Anya said, I'm unfortunately not in California right now, but I am heading up NASA's Irish headquarters here in Belfast. So the first question I always get asked when I tell people that I'm working for NASA is, are we alone? Are there aliens? Is there other life out there? And this is a pretty loaded question because on one hand, there are about 100,000 million stars in our galaxy alone. And then there are millions upon millions of other galaxies, all containing countless numbers of planets and other celestial bodies. So it seems totally impossible that we could be the only life forms in this vast expanse of a universe. But then on the other hand, Earth is really quite special. It satisfies a huge list of factors that allow life to exist here, including our atmosphere and the oxygen we can breathe, our moderate climate, our perfect distance from the sun, our magnetic field, the presence of water, just to name a few. And having all of these stars align, so to speak, is really quite lucky. But what is life anyway? On Earth, we understand life to depend on a number of criteria. Molecularly speaking, we require water, carbon dioxide, and methane. But what if there's other forms of life that we don't understand or haven't seen yet? And what if life is out there right in front of us, but it's not life as we know it? So we're missing it completely. But we're getting ahead of ourselves. So let's take it back to the search for life, or rather the search for other planets. So exoplanets is the name given to planets outside of our solar system. So they're planets that are orbiting a star other than our sun. And these planets are really far away. The closest exoplanet is over 4 light years away. So that's more than 25 trillion miles. So we can hardly go there to check them out and see what they're made of. But if they're so far away, how do we even know that they're there at all? The first exoplanet was discovered in 1992, and since then there have been over 4,000 confirmed by scientists using incredible telescopes. And this image from NASA displays some of those telescopes. So actually this James Webb telescope is being launched in October, and it's hoped to revolutionize the field of exoplanet science and our understanding of the universe in general. But of the existing telescopes, Kepler and TESS have surpassed the rest at finding exoplanets. And that's because they use a method known as the transit method. So the transit method is when we observe an exoplanet passing between its host star and us. So as an exoplanet passes in front of its star, it blocks some of the starlight, causing its brightness to dip. And scientists can detect this dip in brightness and use it to understand a lot of different information about the planet. So first of all, the dip in brightness indicates that there's a planet there at all. Secondly, the percentage of starlight blocked by the planet is proportional to the size of the planet. So we can use this to figure out the planet's radius and its mass. But most importantly, for us at least, is that we can learn what this planet is made of, and that's using a very clever technique known as spectroscopy. So scientists use spectroscopy to understand an exoplanet's composition, or what molecules are present in its atmosphere. So the light that we receive from a planet can be broken down into different wavelengths, just like a rainbow, to produce a spectrum. And the spectrum is essentially the intensity of light at each wavelength, or the brightness of light at each wavelength. And it tells us a lot about the different molecules in the atmosphere. And that's because different molecules absorb light at different wavelengths. So the peaks and troughs in our spectrum will give us clues about what chemicals are in the atmosphere, absorbing and scattering the light to produce the spectrum that we see. So when the telescopes look into the sky and observe a star, it will have its own signature spectrum. So here we have our star, whose light is passing through our spectrometer, which is just a prism here, to produce a spectrum, which is this bumpy line indicating the intensity of each wavelength of light. But when an exoplanet passes in front of that star, the starlight filters through the atmosphere of the planet, and some of the light is absorbed by the different gases and molecules present in that atmosphere. So when we see these black lines and these troughs in the intensity plot, that tells us a bit about what molecules the planet could be made of, different molecules that have caused these spectral features that we see. Okay, but I mentioned clouds and how they can cause problems for observers and planetary scientists. And that's because clouds can heavily impact the spectrum that we see. So if we have an exoplanet with a spectrum as shown, there's a lot of spectral features here. There's a lot of detail in this graph. So that's going to give us a bit of information about the molecules in the planet's atmosphere. However, if there are clouds around the planet, and in particular, if there are a lot of clouds, the spectrum can be essentially featureless or flat, masking the composition of the planet it hides. And this is because clouds can reflect or absorb the light from the star, stopping it from penetrating deep into the atmosphere where it would have been absorbed by the gases that we were hoping to see. Apart from masking the composition entirely, clouds can be menacing in our interpretation of spectral data. So a planet could have a clear spectrum, like so, but when shrouded in clouds can exhibit entirely different behavior. And sometimes that cloudy profile can be very similar to a clear profile of an entirely different planet. So without properly understanding the clouds, we can misinterpret the planetary composition altogether. So how do we account for these clouds? Well, the first thing we have to do is figure out where they form, which is usually at cooler temperatures. And once we know where in the atmosphere the clouds will be, we need to understand how they behave. And this involves a lot of complicated microphysical processes. So looking at very small microscopic scales to see how tiny cloud particles behave. And one of these processes is condensation, which is when vapor condenses into cloud particles. And then the opposite mechanism of evaporation can occur when these cloud particles evaporate back into vapor in the atmosphere. We also have to think about how particles move about. Transport occurs due to diffusion and convection, but also sedimentation or rain from the clouds. Another thing that can happen is coagulation, and that's when smaller particles join together to form bigger particles. And there are many more intricate microphysical processes that call for careful mathematical models to understand and predict. And then we use our understanding of these processes to define a number of critical parameters